Okay, right, today's session is all about sort of geeking out a bit. We're going to show you how to build a content versioning system, okay? So we're going to cover a lot of stuff today, a lot of information to take on board. This is the last lecture that covers the last summative assessment. So this is the last lecture that really matters in terms of getting a good grade. And we're going to finish with a bang on this one. There's a lot to cover. We're going to look at revision control and the why we do it and the different options we've got available to us. We're going to look at Git, which is the probably the best revision control system there is. We're going to build a Git server on the Raspberry Pi. So you're going to take the best revision system in the world and build it onto your Raspberry Pi. And then finally, I'm going to show you how you can clone your repository and clone your version system onto your local computer. So you can always have the latest version of your files, and so you can always have a backup copy of what you've done. Okay, so from this point onwards, there's no need to have zip files, different versions, and all sorts of bits and pieces. Next week's going to be a mixed bag. We're going to talk a little bit about GitHub, which is sort of the commercial implementation of Git. I'm going to talk to you a bit about easy ways to log on to Git and GitHub. I'm going to talk about branches and forks, and we're going to cover a few more advanced Git concepts. And as part of that, I'm going to get a little bit of shell scripting in there as well. Okay, so it's a real mixed bag next week. Then the following week, we go on to the final cycle, which is formative only. We're going to work with Amazon Web Services. Okay, so that's the plan. Right, okay, very quickly. Those are the 4 topics for today. There's quite a bit of information on the slides. Okay, so versioning systems, what do we do at the moment? Well, what we do normally, if we've never heard of versioning systems, is we'd have lots of versions of our files. You might have a backup system. You might zip your project up every night to make sure you've got a version that works. Or you might rename your files. There's my main version, my main C++ file. There's version 5, the latest one I've saved. Okay, there's my previous version. There's a headers file, okay, which is, I've only got one, so I haven't got a version number. Oh no, there's my backup copy, the latest save of the headers file, can you see? So I could just rename my files and have some system. So guys, take your time, make yourselves comfortable. We may overrun this lecture, by the way, because I've interrupted so many times, I won't have enough time to finish. Okay, so what's the problem with this system? Let's go through a few. Right. First problem is, what and why got changed? You've got all these version 4, version 5 files, all these different files floating around the system. What actually changed in each version? You know, what was the modification? Also, if I've got version 1 of one file and version 5 of a different file, which one goes with which? Which header file, which implementation file? You know, what's the relationship between the files? Who made the modification? If you've got 4 people editing the files in your folder, who created version 5? And finally, when you made all these changes, how do you merge everything back together so you've got a working program? So you can see there's lots of little issues here, can't you, that we've got to resolve. Now, the idea is we're going to use something called Git, and Git is a version control system. And what it does, it keeps track of every change we've made to our software, which means we can rewind, we can see who's done what, we can see what changes have happened where. And there's a special tool called Git Blame, which actually allows you to identify who messed things up. So it's a very powerful system. Now, there's 2 ways you can do source management control. The first version is called file lock-in. That was the very early version, and we'll talk about that in a moment. And the second way is called version merging. So there's 2 very different ways of handling version control with our files. So file lock-in, let's start with the file lock-in. This is the earliest version. It's still used by Microsoft. This is their Visual Sourcesafe approach. And I checked last night and they still sell it. I kind of thought it died out about 15 years ago, but I was wrong. So what we've got, the idea is very clever in a way. Only one developer can edit a file at any one time. So if you want to edit main.cpp, you book it out, and it then locks the file on the central server, so no one else can get that file. No one can access it. Until you've finished your changes, you push it back and you unlock it. Almost like when you open the Word document. If you try and open the same document in two places, yeah, it has to be read-only, doesn't it? Yeah, it's the same idea. So it works really well, okay? So no one can make changes until the developer checks it back in and unlocks it. Okay, so there's a little diagram showing what's going on. So computer A checks out a file, locks it, pushes the version back in, unlocks it. Computer B then pulls the file out, makes changes, pushes the file back, and unlocks it. So in a way, it's a perfect system, isn't it? You can't have two people editing the same file at the same time. When the changes get pushed back, the person's name gets attached to that version. So it's very, very simple, and it does work. Okay, problems. If two people have made modifications to the same file, you've got to make sure you're checking out the right version, haven't you? You've got to check out the latest version. What happens if you make some changes to a file and you're not quite finished with it? Do you keep it locked out so no one else can edit the file? Do you unlock a badly coded version to allow someone else to make some changes? So let's say you're working on something, you get stuck, or someone's got a solution. How do you handle that? There's a problem, isn't there? Because if you send it back into the repository, then everyone else gets the bad file. Central server goes down, you really are stuffed. Basically, you can't do any work. And taking work home, in fact, the worst case scenario I had with working with this is we had a guy who left. And when he left, he locked out all the files. There was nothing we could do. We had to trash the entire project. Because no one else could book any files out without him unlocking them. So he basically sabotaged the entire project by just booking out every file on the system. We couldn't do anything about it because basically the account got deleted, therefore there was no login to unlock it with. It was horrible. So basically it kind of put me off this idea of file locking as a mechanism. So I then looked into this. The classic lost internet. If you lose the internet connection, you can't lock the file out. So it only works if you've got a small team in the same office working together on the project and you all know each other and trust each other. So there's a big problems with this. So what happened is they developed a new system called CVS, which I adopted after we had this issue, content versioning system. And this idea is multiple developers can edit the same file at the same time. Now let's think about this for a minute. So that main.cpp file, three of you could book it out. You could all work on the same file and all push your changes back. Okay, kind of magic. And the idea is the first developer to check in their changes wins. So it's in your best interest to keep pushing your changes back to the server, keep pushing them back. Because if you hang on to your files for too long, someone else will have made changes. What's really clever about this, okay, this little diagram to explain it, there's there's my server with the master copy of the repository. And what's clever about this system is you don't just get a copy of the files on your local computer, you get a copy of everything. You get a complete clone of the entire repository. You get a copy of what changes people have made to the files. So if you haven't got an internet connection and you need to roll back to an earlier version, you can do it. Because every change is in your repository on your local computer. Every change ever made, who did it, what they did to it, is all stored locally. So if that suddenly gets wiped out, you've got a complete copy of the entire code base with all the changes. And this person also has a complete copy of the code base. So everyone has a complete copy. It's sort of peer-to-peer. That's the way to think about this file merging approach. And the idea is, there's my file, which I've checked out. The same file I've checked out, there's all the versions stored, what changes every person's made to that file. So I can roll back to the versions, I can check the versions, I can see what other people have done. And when I'm ready, I can push it back. But look at the server, what's missing? What key component is missing from the server version? The files. We'll talk about this a bit later, the server doesn't actually store the files. It stores a hash of the file contents, plus a link to what hash represents which file. So you'll see lots of RSA hashes going on with this. Basically, this is what's called a bare repository, which means there are no files, because the server's never going to edit the files, are they? The server doesn't need to have the files. It needs to have what the files contain and all the versions and the changes to them. It doesn't actually need to store the files. When it downloads the version changes, it can reconstitute the file from those version changes. So it's a very, very clever system. So the idea is every change has a revision number, which is normally a 7-digit, looks like a random hash number. We'll talk about that a bit later as well. Every revision has a timestamp, the person responsible. You can compare the revisions, so you can do what's called a diff, where you can compare two different versions of the same file. You can restore versions. You can roll back to any version you want and create a branch. And you can merge. So let's say you have a version that doesn't work. You go back, you create another branch, and suddenly you find this feature of both branches you want. You can merge them both together again and create a merged version. I mean, the advanced Git is kind of, it hurts your brain sometimes looking at how these things can work. So today's session is all about getting it started, and the lab's all about just getting the basics working. When we talk about it next week, there's lots of really cool features. There's a tool called Pickaxe, there's a tool called Cherry, there's a tool called Diff, there's a tool called Info. Okay, lots of tools which allow you to work with these systems. Okay, issues. What happens if two people make the same change to the same file? As long as they haven't changed the same line of code, it will happily merge the changes together. Does that make sense? It only goes wrong or has an issue or throws a wobbly if two people have edited the same line of code and could try and commit two different versions of the same line. If that ever happens, there's a solution to it. There's a manual way you can actually look at the two versions visually and say, that's the one I want. So it handles almost anything. It's also very bad at binary files, things like photographs and videos. Because it's a text-based versioning system. You can store files, but it has to change the entire file when you make changes to it. Does that make sense? You can't work out which byte of the files, which byte of the image is being changed. It treats it as a blob. And coordinating the team, as long as you trust the people pushing changes to your main repository, it works fine because you can always roll back to the version before if something goes wrong. And there's something called pull changes, which allows someone who's made big changes to a branch to actually request to merge the branch, and then you can look at what they've done and how it compares to what you've got already and decide which bits you want. So why is it so good at working in teams, and why is it working in the peer-to-peer approach? Well, GitHub, which is the one we're looking at, was invented by a guy called Linus Torvalds. Okay, the name should ring some bells. Linus Torvalds, he invented Linux. He wrote the original Linux kernel. He heads the. There are tens of thousands of developers working on the Linux kernel at the same time. This model handles tens of thousands of editors, coders working on the same project, because it scales. Pick up to the previous version. There's my computer A. I can also clone off that. So let's imagine that's in my office, my first office, and that's in my second office. I might have 5 people working in the first office. They could clone off that repository. So you've got this tree structure going down, and they can merge changes back to the computer A, then computer A can merge changes back to the main one. So you haven't got everyone trying to hit the same repository at the same time. That's the key to this. It's distributed. So Git. Fundamentally, Git is the best version control system in the world. And unlike Visual Sourcesafe, it's completely free. It's open source. In fact, the irony is that the Git source code is on GitHub. So if you want to, as long as you've got Git installed, you can download and compile Git. Think about it for a minute. But you need to have Git installed to be able to compile it. So luckily, we have binaries we can install to get ourselves going. And it's designed to track files that frequently change. In other words, when you worked on a project like 321com, for instance, you're all making changes and messing with the code, it can track who's done what and what changes have been made, and it forms a diary of what's happened to that project. And it's fantastic for distributed development. The team members could be sitting in the same office together, but they could be the other side of the world, because it doesn't rely on a consistent, reliable internet connection. Okay, that's a bit small. Okay, keyword is a repository. We call libraries repositories. Okay, that's a key term. So when we have a repository, that's the library of our project files. So let's think how it works. Let's have a quick diagram to kind of visualize things. First of all, there's our master repository. Now, there's nothing special about the master repository. It's just we're calling it the master repository. Okay, that's the important thing. It's almost identical to the clone repository because it's a clone. We just decide that's going to be our master repository, and we protect it with passwords and hashes and so on. And there's our server running that repository. So what we have to do, the first thing we have to do is we have to get a copy of the contents of the repository. And what happens is we call a clone command, and the clone will take a copy of the repository, pull it across, and store it on our local file system. As part of that, it will reconstitute all the files that are part of that project and put them in the folder for you. So when you've pulled a repository, you'll find a special hidden folder called .git, which is all the version control stuff. It's got a dot in front of it because on Linux and Mac, dot means hidden. So it's got a dot so you can't see it. On Windows, unfortunately, it kind of breaks down a bit. If you see a folder called .git, don't touch it, okay? Because that contains that beating heart of your content versioning system. And what it does, so you clone all the .git stuff across, all the hashes and all the paths and routes and stuff, and then it reconstitutes the files on your file system. So you've now got a folder full of files. You know, you might have got .py files, YAML files, all the files to do with your project. And if you're doing, say, Google App Engine, you could actually point Google App Engine to that folder and run your Google App Engine thing locally and test it, because you've got all the files that go with the project. Okay, so that's really clever. So you can build it locally, you can run it locally. If you make changes to your code and you modify the code, you have to commit the changes. And what commit does, it what commit does, it tells the repository what's changed. And the repository, your repository, stores a record of what's changed in those files. And every time you commit, you have to put a message on the commit to explain what you've done. Okay, so every time you commit, you had a little message saying, fix bug 56, got the code working, finally got Google Maps to work. You put a little comment in there to explain what you've done, and that gets committed back to your repository. So at the moment, that contains different files, a different structure from that, doesn't it? Because you've made changes to this. This is now changed. And this hasn't. So if someone now clones their own copy, it won't contain your changes. Okay, it's very important. So when you've committed lots of commits, and you've done 5 or 6 bug fixes, and you've got lots of commits stored up, you can check the status of your repository, so Git Status, and it will list all the things that have changed, and all the commits you've made, and all the messages you've added to it. At that point, you can do a push. And what the push does, it pushes your repository changes and syncs them back to the server, back to the master bare repository. So now, if someone were there now to clone a copy of the repository, your changes would be part of that repository. But if they'd already pulled a copy before you made the changes, they're out of sync, aren't they? You've made changes to the central repository, and they haven't got those changes. So what you should always do before you do any development work is do what's called a pull. And what pull does, it finds any changes here that aren't in your repository and pulls them through to your local repository. Do you understand what's going on? You see how these work together? So it means you could have, you're going to build a master repository on your Raspberry Pi, and you're going to build a clone repository on your computer. Or if you wanted to, you could have a first Raspberry Pi with your master repository and have a second Raspberry Pi as your clone and clone the files across. Now, when I said the .git folder is verboten, you shouldn't touch it, you shouldn't do anything with it, it's not quite true, because I think it's useful, especially when you get your head around the basics, to look inside it and look at the file structures. And then when you make a commit, see what's changed. To have a really good understanding of what's going on behind the scenes. But if you just want to get the basics done and get the job done, just don't touch the folder and everything's fine. What happens if you mess that up? If you mess up that clone repository, it's very simple. All you've got to do is just delete the repository and clone. And that gives you a fresh repository, doesn't it? A fresh copy. As long as you haven't made any changes to your local files. So the key here is this master repository. And the word master, upstream, it's sometimes called upstream repository, it's called main repository, parent repository. I just call it master because it's a convenient term. The trick is that the main repository, you should not be editing any files on your main repository, should you? It's not for editing files, it's for version tracking. So we create a bare repository, which means it never gets any files stored. There's never any physical files stored on the system. It's simply the changes. And all the purpose of the master repository, all it's there for to do, is to make sure that you keep your clones in sync with each other. That's its purpose. Okay, so you should never be directly editing that master repository. In fact, when you set one up, you make the first changes from your local machine. You never directly edit it, ever. The clone repository has a copy of the files which it reconstitutes from the hashes. It contains a record of all the changes, and this is most important, it contains something which the master one doesn't contain. It contains the link to the master repository. So when you push your changes back, it knows where to push them to. Okay? So it knows where it should be pushing the changes. You haven't got to tell it each time. And of course, because it's a Linux-based system, everything's text files. So if you go into your, if you were to look in the .git folder, you would see a whole series of hashes, blobs, and text files. And you can tweak the configuration by just opening the text files and manually changing things. There is a config file in there, just like for Apache, for MySQL, for PHP. Yeah, it has its own config file, and you can tweak that and you can change the master repository. It's very useful. Let's imagine if the master disappears and goes, and you need to point to a different master. You need to be able to change that path so you can point to the new master repository. Okay, the files aren't on the server. Where are the files? Well, the basic idea is a blob. And what it does, it takes every file that's committed, that's pushed to the server, or committed. It generates an SHA-1 hash of that file, and any file can be represented by a unique 40-character hash. And all it does, it stores the hashes without the file names. Then it has a lookup table that says this hash matches this file name in this folder. And the clever thing is, because the hash is so small that it can store lots of files in quite a small space, if two files contain the same thing, it simply just puts another pointer to the same hash. If two files are very similar, the hashes are very similar, it stores the difference between the hashes to save space. So it's very, very compact, the way it stores this. And you see lots of long hashes. Every time you commit a file, there's a long hash associated with it. And also there's a long hash associated with every commit you make, the actual commit process. So you've got folders and folders full of random 40-character strings. And that's it. They represent files, they represent folders, they represent changes, and so on. And what's important is, within the scope of your project, every hash is unique in terms of what it contains, but the uniqueness can be identified for the file name within the first 7 characters. So when we compare hashes, we only need to input the first 7 characters, and it can work out the rest for us. And you'll see this all the time. There you are. That's the folder structure. That's my blobs. These numbers here are the start of the hashes, and that's because in 32-bit systems there's a limit to how long the hash can be. So it takes the first 2 digits of the hash and turns it into a folder, so it can scale properly. So that 0881 blah 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 represents a unique file on the system. That's another file. Info represents the structures of your project, and pack represents the changes. Does that make sense? So it stores everything in these funny long characters, but it means it's a very efficient storage system. Right, now we get onto the nuts and bolts. What you're going to be doing is you're going to be creating the bare master Git repository on your Raspberry Pi. You're going to give developers remote access. You're going to set up your users to allow them to push and pull and clone from your repository. Okay, so you've got the usual passwords. And we're going to allow push and pull, so everyone who's a developer can clone, push, pull, commit, and so on. Right. Normally, all you need to install is Git core. So the whole of the Git system takes up 21.5K. That's it. That's the entire Git server, or Git's client. Because remember, it's peer-to-peer, so the server and client are the same thing. Occasionally, it installs Git as well as part of Git core, but I think the actual, you don't need this anymore. I think Git core does everything nowadays. Now, hosting the master repository. You've got to put the repository somewhere, haven't you, on your server? Somewhere you remember. Now, remember how the website was var www? Okay? I tend to put var git as my Git folder, because then my website's in one folder, my Git repository is in a different folder, all off the var folder. And also permissions are pretty straightforward. And that's going to contain all our master repositories. So if we've got 5 repositories on there, it might be git/bookshop, git/tourism, git/321com. Yep, they all sit in the same folder. The trick is though, once we set this up, we're never ever going to look in that folder again. Yeah, we never care about the exact contents because it handles it for us. Now, all our developers need access to that repository. Okay, so the obvious choice is a group, isn't it? Yeah, because all our developers need access to that folder. We don't want to give everyone access to that folder. Remember our Linux groups? So the logical way to do it is to create a new group, call it developers or Git or something, and add all the users, the editors who need to have access to the repositories, to that group. And that would solve the problem, wouldn't it? It means everyone has access to the folder without, everyone who needs to have access has access to the folder. Okay, now this is the bit which Windows users will find very, very confusing. Okay? Let's imagine, forget that word. I want the folder that contains my individual repositories must have a .git extension. The folder. It's not a file, it's a folder. This will confuse you if you're used to Windows where extensions relate to files. That's just a character. Yeah? And that means when we start pulling the stuff through, the file we pull through is actually the folder name, and it means we can pull something through called .git when we clone our repository. It just makes more sense. So the folder should have a Git extension. So my folder is called website.git, for the example. But it's a folder, not a file. And then when we go into the folder, we create a bare repository. And that's all we do. That's the command. That's all we need to do to create a new repository. Git init. That's a long flag, with the 2 dashes, which means we put a word in rather than a letter. Bare means we don't want any files in there. If we left that bare off, it would create the folder structure as well. Shared equals group, which basically means we're going to share it out amongst a group of people. It's a shared repository. So that's how we create our repository. Once we've run that command, everything's fine. We have a bare repository. And if you look inside it, that's the structure we have inside our repository. Because there are no files in this repository, there's no .git folder. The .git folder contents are in our folder. Because we're not messing with files, it doesn't create a hidden .git folder with all the special bits in. It simply places these folders inside the .git folder, the website.git. So let's have a look at this. Branches, forget branches. Config, there's your settings. So if you want to make changes to the way it works, you can edit the config file in there. Description, you can have graphical front ends, like Git Diff, for example. That contains all the information, the extra bits of information that's required by the graphical front end. Head is the current, latest version. And that's simply a symlink, a pointer to the correct reference in our repositories. That's just an update. That's just the latest build. Hooks are really cool, and we may talk about these next week. Hooks, you can run scripts, bash scripts, shell scripts. You can trigger them with different actions. So you could trigger a script when you push a change to the server. You can trigger a script when someone pulls or someone clones. So you can run arbitrary bits of script when events happen on the repository. So example, on my server, what I've got a nice script which every time someone commits a change to the repository, it zips the files up, transfers them to the website, and unzips them after deleting the current contents. And that's just a 5-line bash script which sits in the hooks folder. So you can do all sorts of really cool automated stuff with this. Forget info. Objects is where the blobs are stored. And refs is a link to all the changes and all the bits that have taken place. So this is typical Linux. This is all basically text files. Now, don't forget, if you allow users access to your Git folder, you must make sure you've changed the group permissions. Makes sense, doesn't it? If you added everyone to the Git group, you've got to make sure that they have the correct permissions, and they need to be able to read and write. They do not require execute permissions. So what's that in Unix terms? What number is that? 6. They need 6. Yeah? R, W, but no X. And make sure that when you create the repository, you do a chmod on the contents of the repository and make sure you recurse down to the bottom. So they've got read and write access to everything. Otherwise, this just won't work. Now, this is the trick. When people connect up, they can only see their home directory. That's their home folder, isn't it? Even though they've got access in /var/git, they haven't got permissions to get to that Git folder. Because the var folder, they haven't got permissions on. So we need to give them a shortcut to the Git folder so they can see the repository. Okay, you understand that? They've got to have a shortcut to the folder. So in their home folder, like having a shortcut on your desktop, where you double click it goes to the right folder, we're going to create a shortcut in their home folder to point to the Git folder. Okay, so it's almost as if all the files, all the Git folders are in their home folder. Okay?
Hello.
Right? Yes, that's all right. That's okay, yeah. Yes. Now what I've done, I've asked, we've got this, so if I stop what I'm doing for minutes, yeah, you can do, do you want to do a little talk? Or do you want to sit here 5 minutes and have a...
I'll get the gist of it.
Yeah, okay. So the idea is we create a link, a symbolic link, from our project folder to our home folder. Okay, is that making sense? We create a shortcut across there, and then when I list the contents of my home folder, look, there's the name of the Git file folder, and that's what it's pointing to. So if you look at my command, you can see that I've created a symbolic link called raspberrypi.git, which points to my website.git folder in the var folder. Okay, that's clever because once you've done that, you can clone it. Okay, so the idea is we're going to pull the copy down. We install Git on our computer. Okay, so usual installation. Now this is important. When you commit changes, there is a name and an email address associated with the changes that you've made. So if you call the config command and set your name and your email address correctly, every time you push a change to the repository, it will be flagged up with your name and your email address. There you are. That's how I clone from my Raspberry Pi. That's it. So there's my username. There's my, because obviously IT services didn't give us static IP addresses. Okay, so there's my domain name. There's the address of my server. There's the colon. There's my Git folder, which is a shortcut, really, isn't it? And that's the name I want to call the repository on my local computer. So when I look at my repository on my local computer, it'll be the folder called RPI website, and it points to this master repository. So I've cloned that onto my local computer. You know, and it says blah blah, cloning to the website, ask for your password, checking connectivity, done. And we now have a little folder on our computer which contains our project files. Okay, we've talked about the Git folder. Now, if you run this command git remote, it tells you what connectivity you have for your repository. And you can see here we have a fetch permissions to that repository, and we have a push permission to that repository. So it's always good to just double check that to make sure you've got permissions to push and pull. Now, what we're going to do, let's imagine we add a new file, and the classic one is a README file. So we create a text file in that project folder, that Raspberry Pi folder. We put some text in it, and then we save it. There's my file. Now, first thing we need to do is we need to tell our local repository we want to add some files. So we could say git add readme.md. But what you're best doing is choosing git add dot, which basically adds all the files in your commit repository to the next commit. Okay, that makes sure everything's there. Then it's worth checking to make sure you've got the right files in your commit. So you type in Git Status, and that will list any files that are part of the next commit. It will show you any file change, any added files, any deleted files. And then you run this command, git commit. Remember, this is going to commit to our local clone. And there's my message. And that's going to push the changes to my local repository. Nothing's happened to the server so far. Nothing at all. Until, oops. There we are, that's the process going through. Sorry, that's just a screen so you can see what's going to happen, what it look like. And finally, this is how we push our changes through to the master copy. Git push, origin is the name it's given to our local copy. And if you look at the .git folder, you'll see that mentioned. Master is the branch that we're pushing to on the server. And until we talk about branches next week, that won't make a huge amount of sense. And as soon as we do that, all the changes that were on our local computer have now been pushed through to our master repository. Like that. You know, it's easy, look. Git status, change it to be committed. There's my new file, readme. And git commit, one file changed, 5 insertions, push, 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 master to master, and it's done. And what you've got to do for your assignment is you're going to be able to create a second local clone repository, and you're going to practice pushing and pulling between the two repositories to make sure that any changes are being pulled and pushed through. Now, perfect timing.
Right.
Okay, because I've asked someone who actually uses repositories on a regular basis to come and talk to you. You'll introduce yourself. And
So I'm Dan Fisher. I'm the software development manager from IT Services. I'm in low road. We're responsible for techies and their dealings with IP addresses.
do you want the microphone? Would that be useful?
Oh, yeah. This is way more scary than I
Yeah.
thought. We don't actually use Git, but we use Subversion.
Which I believe is the precursor to Git, wasn't it?
Yeah, very, very similar model. All the principles apply. Subversion of Git, I believe, is much better suited to distributed development. Sorry, do you want to talk about?
Yeah, talk about how you use it and how you work in a team with it. That'd be
Yeah, fine. Okay. You haven't talked about branching yet.
not branching. I mean, if you want to mention branching, that's fine. That'll be extra
Yeah,
information.
Okay. Well, I mean, branching is a maybe it's best to start with it, but these kinds of systems are collaborative, non-locking systems, and traditionally version control systems have been based on taking locks out of files. So a developer says, I want that file, it's locked, only I can change it. And until they've committed it back to the repository, nobody else can touch it. That has a number of issues, not least that people check out files and then leave, which is a bit of a mess. So this way of working is much better because it's service what they do all at the moment. Well, actually, no, it doesn't really know anything.
You might have to raise your voice a bit because I've.
The server isn't particularly aware of what you're doing to the file locally. Locally, you can track all the changes you've made to the file since you last got it from the server. or somebody else who may be working on the same file. Because the second person's commit, or any subsequent commit, can result in conflict. I'm not sure about Git. I'm sure it's even better than Subversion. Subversion is very good at reconciling differences between files and merging them. And that's almost always done automatically for you. So you both change the file. You may find some lines, somebody else may have taken out some lines have been changed. It works out what's different and produces one file as a result of those changes. It can happen that you get a conflict, and in that case, you need to sit down with the person whose code changes you're conflicted with, and actually talk about what the result needs to be, what the output needs to be in the end. And I find that's quite a good way of working in a team, because it does bring people together and talk about changes like that and the same stuff, rather than people being isolated, which can happen with the older model. The older model, which I believe Microsoft potentiated.
Still available at cost. Visual Sourcesafe, remember that one?
Yeah, so it's a good model. It's great. It's great working in the off system, because the server doesn't care what you're doing, particularly until you commit the stuff back to the repository. It doesn't matter whether you're on the network or not. So I can go home today and continue working on the code. It doesn't matter. I can come back tomorrow and connect and push it all back to the file. With the older model, you have to get that out to the service, and then hence you have to be connected to the server.
Okay, so how big's your team? How many people are on your team on the same project?
That would generally be about 8, 10 people working on the same.
And it works quite well?
Yeah.
The Subversion?
The place it doesn't work well is where people are making the transition between the old model and the new, and they don't realise that they should be hanging on to things. But none of you will have that problem, I imagine.
No, you're starting afresh with this, because they've got to build their own Git server as part of this.
Right.
Which should be good.
Yeah.
But we also got private repositories on GitHub. So we've got 125 repositories, private repositories available. So do you use GitHub at all for any of your work, or?
We don't, no.
So you've got your own local Subversion server?
We keep Subversion here also.
Okay. If any of you want to work in a team on projects, then you've got two choices. You can either work on the Raspberry Pi and build something around there, or if you want to, come speak to me and I can give you a private GitHub repository to work on. Next week, I think I'm going to talk about branching and conflicts. Right. Next week, okay. Where it puts the markers in the code, and does Subversion do the same thing? It kind of marks the code and shows you what the different things are.
Yeah, merging.
Yes.
That's a good one.
Yes.
And tags we use as well.
We'll talk about tags. Okay, so I'll have that to the list for next week. Tagging, branching, merging. That's pretty much the main stuff, isn't it? There's a lot of very specialist tools in there. The blame tool, I particularly. It's not quite as nasty as it sounds. What it does, you look at one file and you can see every change that's been made to that one file. Okay, so if one file's not working, you can literally see every single thing that's happened to it. So it blames a bit of a negative connotation, but it's more about just seeing who's done what to a file. Yeah. The good thing about this, about using Git, is you've got to keep records of what you've done for 321 for your project work. You've got to have a diary, you've got to write a report on this. But if you're tagging your commits, then basically you've got a complete record of everything you've done, haven't you? All the changes, everything you've done. In fact, I've been earwigging on some of the GitHub projects. And last night there was a problem with one of the teams working through a problem. You could see all the issues bouncing backwards and forwards. There was an issue raised, somebody flagged up some extra comments, and the final thing before about 2 o'clock in the morning was fixed, resolved.
Right. Yeah, and it was well worth putting comments with your commits.
Well, I don't think you can commit without a comment. No, we're not on Git. If you try and commit without a comment, what it will do, it will pop up your favourite editor, which I think is defaults to Nano on the Raspberry Pis, and force you to put something in. It's a good idea to put a comment anyway, because it helps tracking the changes. So Subversion, I think basically Linus Torvalds, who wrote Git, based it on Subversion anyway. I think that was his starting point.
Right. Okay. I mean, what you've been talking about here is very similar.
Yeah. Okay. Thank you very much for that.
Okay.
Thanks for coming to talk to us.
You're welcome.
Okay. Cheers. Okay. Cheers. Okay. Okay. So basically, that was all about. It's really used. So the university uses Subversion rather than Git. but subversion is just a precursor to Git. It's the same concept. So we've cloned down. We can have a copy. Now look, when you clone the second time, I've got a folder called RP website 2. You can see now I've got count objects 3, total 3, delta 0 means there's changes 0, receiving objects, checking connectivity, and I can now make a change in my second repository. I can push the changes through, git add, remember git status, git commit, yeah, push the changes back through, git push origin master, counting objects 5 done, compressing objects, so it tar zips them up before it submits them, adds them all up. Now, this is the key at the bottom. That's what I'm aiming towards. See those two funny strings? That's these first 7 characters of the previous version, the version it had before, the version it's updating. Those are the 7 characters for the latest commit. So if I want to compare the two, I can use those as my tags to compare the two commits. Does that make sense? The idea with tags, which we'll talk about in more detail next week, is I can put an alias on any of those commits. I could call it v1, v0.0.1, for instance, on one of them, or v0.3.4. So I can simply attach an arbitrary string to represent each of these commit hashes, which means when I'm tracking things, I can see version numbers rather than the 7 character hashes. Okay, so I've taken my second repository, I've made some changes, I've pushed them back to the master, and now my first repository, I want to make some more changes. Before I do any changes, I must call git pull. If I do git pull, it will pull down all the changes my second editor's made into my repository so I can see the changes. If I don't git pull, there's a risk that the lines I'm changing have already been changed on the server. So it's very important you git pull as a matter of course before you do any editing on the project. And as you can see, look, can you see? Git pull, 5 done, and you can see, look, updating, and there's the hash that the first person submitted. So it's updated my version to the same version that the last person edited. Okay, and the fast forward, blah, 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 you can see that the second editor added 2 lines to the README file and deleted 1 line. Even just in the summary, you can see what's happened. If you use GitHub, you get red squares and green squares to represent those numbers. So those little pluses and minuses, you can see, look, 2 insertions. There's the README file. So in the README file, since I last looked at it, there's been 3 changes, 2 insertions, and 1 deletion. It even tells us there, look, at the bottom. So it's quite concise detail, isn't it? It's quite a lot of detail there. So there's our hashes. There's the previous hash, there's the current hash. If I want to see the difference between them, I simply call Git Diff and put that in. And it will tell me, there you are, there's the differences. So let's look carefully at this. Okay, the first file is README, the second file is README. Can you see I've added that line, and I've deleted that line. It's in red and it's got a minus at the beginning. Plus means added, minus means deleted. So the 3 changes were, the 2 additions was a blank line and my comment, and the deletion was the previous person's name. So nothing is thrown away. Everything is available for you to look at. There's nowhere to hide with code. Now the lab tasks, it's the last thing I'm going to talk to you about today. I've updated the task 5, okay, to simplify things a bit. I've made it easier for you. I've simplified task 5 a lot. You're going to install Git and create a Git folder as your first task, first part. Develop a group with two users. Now the users might already exist. They might already be part of the server, yes? Because you built some users as part of task 1. Yeah, you built a couple of users. Recycle the same users. Create a bare repository with symlinks to the users' home folders. Clone to, I'll call it local 1 so you can explain there's 2 local clones. Clone to local 1, add some files, commit and push them. Clone to local 2 and edit, commit and push, so you get to see what it looks like when there's a file being added, or what it looks like when there's been a file edited. And then go back to local 1 and just pull the changes back and do a pull to see what the changes are. That will get you comfortable with the basics of Git. Now, if when you're working with your Windows computer, you're having problems with it, Git's not installed, there's a problem with this, there's no reason why you can't create your local repositories on the second Raspberry Pi. Okay, so you've got a fallback position if you're having problems with Windows computers with cloning stuff and creating local copies. If you want to, I'm more than happy for you to use a second Raspberry Pi for your clone to create your local copies, because the process is the same on every platform. There's one book on Git. It goes into a huge amount of detail, so if you're really getting into it, that's quite useful. But better than that, there's a free book online. There's a pack publishing book which you can buy a hard copy of, but it's open source. So that gitscm.com book is a free book on Git, and it's really good. Now, I learned a huge amount from that. The previous one, the Git book, goes into a lot more detail, but for what we're doing, that's enough detail there. Either buying the paperback or just looking at it online. And then I've got a couple of references to Introduction to Git, a couple of articles on creating Git repositories and Raspberry Pis, because I learned from somewhere. And that's it. So that's your fifth and final task. Now remember, your assignment's not due in for a few more weeks. You've got 3 weeks left to get this finished off, haven't you? So there's plenty of time. I want time for you to fail. Not fail the assignment, I want time for you to fail the tasks. Because the best way to learn is to do something and to fail. Because then you learn, you make some notes, and next time you do it right. So extra time means you've got a bit of a breather in terms of you can afford time. You haven't got to start panicking when things go wrong. Because these are computers, things will go wrong. Guaranteed. Every time. Without fail. Especially about 10 minutes before the end of a lab. That's when things generally go badly wrong. So work through this. The next week will be kind of rounding things off. Capstone bits and pieces, covering some advanced topics like branches and tags. I must mention tags. Yeah? And I'll cover a bit of scripting. We'll talk about GitHub as well, which is the web fancy sort of commercial version. And that will finish off this task. And then we're into Amazon Web Services. Okay? For that, if you want to go through the tasks on your own and go through the process yourself, you don't have to. This is a formative assessment. You will need to make sure you have an account with Amazon. Whether you've bought something on Amazon in the past, as long as you have an account registered with Amazon, you'll be fine. Because you get the first server for free for 12 months, but you have to have a current Amazon account to do it. That makes sense. You don't have to go through this process. You can come to the lectures and listen in. You can miss the lectures if you want to. If you're not interested at all, you can come to the lectures and listen to the lectures, and then just don't do any labs. You can come to the lectures and then have a go at labs, but don't submit the work. That's fine as well. Or you can go through the whole process. The purpose of the last assignment is formative. It allows you to know where you're going wrong. It gives you some feedback on what you've learnt. So I'll be publishing that assignment in about a week or so's time, probably to coincide with the first lecture of the final cycle. Okay? And thank you very much. Assignment's due in 3 weeks' time, plenty of time. Okay, cheers.